Howdy, everybody. Hope you're doing well wherever, whenever you are. We're here solving Advent to Code Day 13 for year 2015. Um, just before we get started, as always, love to hear your comments and questions you have. I think a lot of them are really great, right? They've been ways to maybe improve my own code, or maybe make me think about different solutions and stuff like that. So keep them coming, and I think this is a great way to get started. I've been reading a little bit about competitive programming. Maybe some of the days we'll start to try and do like see how fast I can solve it. um, I don't know that that's totally fun. I do like watching competitive people solve it, but it's often very quiet. Of course, I'm very quiet sometimes too. So anyway, um, that's neither here nor there. Maybe it'll be something eventually we get to. So I guess it is possibly there. Um, anyway, let's just get started. You'll notice I have a different account. I have something wrong with my other account, so I'll try and fix it. And ooh, that reminds me, the puzzle input is possibly different, so um, I'll need to remember to change that. But let's just get started. We'll read through it, and then we'll get going. So it is Knights of the Dinner Table. In years past, the holiday feast with your family hasn't gone so well. Not everyone gets along. This year, you resolve will be different. You're going to find the optimal seating arrangement and avoid all those awkward conversations. You start by writing up a list of everyone invited and the amount their happiness would increase or decrease if they were to find themselves sitting next to each other person. You have a circular table that will be just big enough to fit everyone comfortably. And so each person will have exactly two neighbors. For example, suppose you have only 4 attendees planned and you calculate their potential happiness. Okay, so it has like, here's the Alice ones and whether they would gain or lose happiness by who they're sitting next to. So this one has Alice, Bob, Carol, and David. Uh, okay. Then, if you seat Alice next to David, Alice would lose 2 happiness units because David talks so much, but David would gain 46 units because Alice is such a good listener, for a total change of 44. Alice sitting next to Bob. No, David. Alice sitting next to David is -2. And David sitting next to Alice is +46. So that does change. Uh, it's like the sum of these two, right? +46 -2 is 44. If you continue around the table, you could then seat Bob next to Alice. Finally, seat Carol. And the arrangement would look like this: Bob, Alice, David, Carol. Okay. After trying every other seating arrangement in this hypothetical scenario, you find that this one is the most optimal with a total change of happiness of 330. What is the total change of happiness for the optimal seating arrangement of the actual guest list? Okay. I think this is a traveling salesman problem in disguise. Like it doesn't look like it, and it kind of like, I think this could lead you to think it's a dynamic programming problem, but I actually think it's a traveling salesman problem. Think about the problem we solved just a few days ago, where it was, can you find the optimal path to all the cities? And you you can pick any start and end location. Like, that's essentially what we're doing here, right? Is we're saying put any person at the beginning and any person at the end, and then place all the people in between and like see what the smallest is. What is the, or wait, uh we want to get the highest, right? Yeah, we want to get the high. So in this case, it's like the traveling salesman in reverse. I guess we did it in reverse in that day 9 too, anyway, right? So I I honestly think this is probably the traveling salesman problem again. It really feels like it, which may make this day somewhat boring. I'm just trying to think in my mind. Yeah, I mean, this is really just, if you think about like Carol to Dave and Dave to Carol, this is really just saying like what is the cost from Dave to Carol, and there happens to be two values in here that represent the total cost, right? So the total cost of going from here to here, uh, is requires you to look like from Alice to Bob and then from Bob to Alice to get the total. And we're looking to maximize that value. And I don't think there's any way you can do this by the traveling salesman. I could be wrong, but mm, I don't see another way to do it. And it's quite possible that, let's just one, two, six. And there's only 8 people. I should copy this right now while I have it. Maybe I do have the same one. It looks like maybe I have the same problem. Do I have it all? Mallory 7, Alice 54. Okay. Yeah, again, there's only 8. And so I think even if it's not a traveling salesman problem, it's probably not worth trying to sorry. I'm trying to do 2 things at once. There's because there's only 8, you probably don't net much by uh even if you could solve it in a dynamic programming way. I don't think there's a way to do it. So let's just try solving part 1, see how we get in there. So I think what we want to do first for solving it is parsing. Let's write a parse function because we use it a lot. And what are we going to get? We're going to get a hash map of stir to usize probably. Oh, I did that wrong. Like that. And then we want to input dot lines dot oh, it's already an iter, so we just want to map L. Ooh, I think I want a flat map because we want to return. Oh no, I don't want a flat map on this one. The other one I did because you could go either direction, but in this case I'm just going to map Alice 54 Bob. Oh, I need to track gain and lose as well. So I'm going to go let parts equal L dot split white space dot collect as a vector, and we'll say like let negate equal match 0, 1, 2 parts 2 gain is +1, or is, I guess just 1. Otherwise, it will be -1. So this is going to be our negator. We're going to say, we're going to parse this integer, and then we'll just multiply it by this when we return the value. So the return value is then going to be parts 0 and parts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I just noticed there's a period there as well. And then parts 0, 1, 2, 3. So 3 dot parse times negate. Something like that. What doesn't it like? Oh, I need to unwrap this. Do I probably have to collect? Okay. Yeah, it's not gonna like this. I need to do like. Oh, I can't return a U size because they could be negative, huh? Okay. What was it? That was the issue? Oh, the period at the end. How do we do that? Can I just do like. Nope. Trim on what? Dot? What doesn't like about this? Trim end matches? Is that what it is? Okay. So what is this parse doing is we're taking each line, we're mapping each of those lines to this. We split by white space and collect, so we get all the pieces. We check 0, 1, 2, the second part, this one right here, to see if it's gain or loss or lose, right? I guess we only need to look for gain, right? We say if it's gain, it's 1. If it's not, it's -1. And then we're going to return part 0 and part 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 with the period trimmed off as like the key to the hash map. And then we'll parse part 3, which is this right here. We'll turn it into an integer and add our negate right here. So that's going to give us a hash map that we can look up and say, okay, if I have Alice and Bob next to each other, can I look that up and see what their thing is? Do I want to do the total happiness here? Probably not. I was just thinking there's a potential for me to say, do I try and find them here, find both ways, or include both ways? I don't think it's worth it. Again, there's not a lot of them. If there were like a billion of them, you may want to do some pre-parsing. And if there were a billion, there's no way we could even do this, I don't think. At least efficiently. But let's see. So we'll say let so we'll have some happiness index. And then we just want to go through each permutation and find the largest. Okay, so we do need each of the people as well. So let people equal happiness index dot keys. We want to get all of the people. So we'll map this. I think it's like this, right? We've done this enough times that it's keys. Doesn't like here. Okay. So now we have the list of people, and we'll use. I think we can just use my permutation thing. Not only that, but I think we can just do the rest of this in an iter, or sorry, in a functional style way. So we can do permutations, new people.len, dot map, p. We'll worry about that later. And we want to do max of these values, right? Dot unwrap. That presumably gives us an eye size. Okay, so now we just need to figure out how to add all the values up, right? So we're going to go through all the people. We're going to find the max. So now we just need to unwrap. Or now we need to take the permutation and figure out the size, right? Figure out the, not the size, but the happiness, right? So we just start. Oh, we can do windows and go. So p dot windows of size 2 dot map the w, and for each, so for each, basically we're going to take two people, right? So in our problem we had like Bob and Alice, and we want to find the sum of Bob to Alice and Alice to Bob, and that's going to be the value. So it's going to be happiness index dot get of people W0, right? And people W1 plus the other way around. That. What doesn't like about this? Expected type eye size. Huh? Mismatched types because of return type. What is this returning? This is an eye size. The trait ord is not satisfied. So we have permutations. We're going to map each permutation to a p. Oh, I need to do a dot sum. There we go. So we're going to create windows of 2. So it'll be Bob to Alice. And we'll say, give me the happiness index of Bob to Alice and then Alice to Bob. And we go all the way around. Oh, but we don't have... that will not do Carol to Bob. And Bob to Carol. Can I do like a dot chain once? Oops, no, it's not rayon. Did I just add rayon? Just want to do standard iter once. And it would be P0, P people.lane -1, like that. Type mismatch resolving once. U size 2. Oh, because I'm doing this, it knows it's of size 2. I think there's a way to do it like this. Does that make it worse? Cannot find this. Something's wrong here. I got it stuck in a loop. $36. This returns none. Uh, Carol David. We want to print people W0 and people W1. George to George. Why would that be the case? Is it this chain? Is this chain not working? Nope. That's not it. Oh, maybe. Okay, let's just print the people. Oh, okay. I'm not uniquifying it. So I should just use a hash set here. Ooh, but I do need to. I definitely want it. I want it to be a vector so I can index it. Don't think you can. Yeah, we just turn it into a. There may be a better way to do this. If anyone knows, like to have a unique vector, uh, I think hash set is just the easiest. These two lines are probably the easiest way to do it. You could potentially do it yourself again because it's really small, but whoa, okay, yeah. Now I don't want it to print anymore. It looks like it's not blowing up. So 709. There we go. Continue to part two. Okay, so that wasn't too bad. I think what did I struggle with? I mean, I definitely had a bug, right? I wasn't uniquifying the keys that I was reading. What would be a good way to remember to do that? Like, it should have been obvious that, oh, this happiness index is going to have Alice on the left hand side 8 times and Bob 8 times. So I need to get a hash set of it. I think I've done this before, right? Where anyway, if you have a better way of doing this, this would be interesting to know. Get like a unique list of the keys. Oh, the other way we could have done it is we could have done like a hash set of a hash set, and then this would have definitely been unique, right? This would have been unique. Oops, what did I do there? So that would have been a potential way to solve that problem. This stuff I'm always not familiar with. If you read this, it looks terrible, right? Um, it doesn't look very readable, but like what you're saying is, okay, create a list of windows, and then we're going to use this chain function, which is a really cool function. It basically says, give me another thing that I can iterate over, and I'll do it after the first iterator finishes. Um, and so this is really cool when you have like you want to like use one iterator after the other, which I think we've done in other problems before. But in this case, it's really useful because the normal windows, it was only gonna like here is the issue is like if we do the windows for this one, it's gonna do Bob to Alice, then Alice to David, then David to Carol, but it's not gonna do Carol to Bob. And so you have to figure that part out, right? And once you figure it, and chain is an easy way to do that. This syntax is terrible, right? I don't know if there's a better way to do this because we're kind of like building it live within the loop here. But the idea is we're saying create an iterator that one runs once on this given list, and the given list is just a single array of the first and the last value. But I don't know if you saw the issue I was having is this right here. I don't know if it'll ever show it. Yeah, this right here. No, this doesn't show it. It was actually an actual array and not a slice or a vector because it knew the size at compile time. It knew it was an I size of length 2, and that's not the same as like a pointer to a slice of U size. So you have to slice it, which is what this does, and then you have to take a reference to that slice to give it to ones. And so this, you know, indistinguishable from magic in my opinion. But I've used this before somewhere, and so I kind of knew about it. You could probably ask AI, how do I chain a static iter that I've or a static value that I've created at runtime, and it would probably show you something similar to this. Um, anyway, so I think those were the only things. So let's move on to part two. Part two. By the way, if you see me over here, I have a little thing that's recording it. I can probably show it in the thing now. So it's right here. I'm trying to track how long it takes me to do each part. Anyway, uh, part of it's just for me, so I can see the times easier. But I also eventually have been thinking about doing competitive programming stuff, so I wanted to create a little app to do that. Anyway, let's back to part two. In all the commotion, you realize you forgot to seat yourself. Okay, so I had myself. At this point, you're pretty apathetic towards the whole thing, and your happiness wouldn't really go up or down regardless of who you sit next to. You assume everyone else would be just as ambivalent about sitting next to you, too. So you add yourself to the list and give all happiness relationships that involve you a score of 0. What is the total change of happiness for the optimal seating arrangement that actually includes yourself? Okay, so this is just part one, but I'm only including, or I'm also including myself. We'll just yoink that, paste that. Oops. So how does this change? Like, I'm pretty sure I can just do like, make this mutable. We'll just do people dot push me like that. It won't be in the happiness index. So down here we can just do an unwrap or 0. Like that. What doesn't it like here? Oh, I need to put a reference. Like that. Okay, I'm fairly sure this works. Like, well, let's run it and see. How many times have I said fairly sure and then it hasn't worked? 668. That's the right answer. Okay. Yeah, this. Okay, so part two wasn't too hard. What changed? We add me, which is now we have 9 in the list, but we're still doing a permutations over it. So what changes then in the code? We basically just say, oh, add me to the list and do this permutation. And the only thing I changed is, so normally you can you do a get and it will return an error, like a or sorry, none if it's not found, right? It'll return none if it's not found. So we just call unwrap or return a 0. So if get returns none, this will return 0 as opposed to an error. And so whenever it's saying, hey, look up the happiness index of anything that I'm in, just return 0 and get it back. So the code is actually quite similar. In fact, it's potentially identical. At least this part is definitely identical. This part right here. And then this part can be identical. I guess it's this part right here. So the only difference is, I'm just thinking about optimizations are like right here and right here. So anyway, there you go. There's part two. I don't think the day was very hard. Again, because we'd already done day 9, it was pretty easy. I'm almost sure. I mean, someone correct me if I'm wrong, but I'm almost sure this is another one of the this is a traveling salesman problem. And even at 9, that's not a lot, right? Like, we're still only like 362,000 operations. Or I think we had done 8 before, right? Is 40,000. So you're still not in the range. Like, I think you probably have to get into like the 12, 13 range. And we complete both of them really quick. Part 1 is so quick, I don't think anything will help. You could potentially, for part 2, we could try to do a par iter on part 2. I think it's like bridge, par bridge. Is it literally just par bridge? No, what else do I have to do? What's it saying? Use rayon interparallel iterator. Okay. This one. Okay, so what am I doing here? I'm just saying, is it is there a potential for me to do this in a par iter? Oh, and I totally did it in part 1 instead of part 2. I'm almost positive it's not going to help part 1, but it might be worth it for part 2. Let's just see if that changes it. No, potentially makes it worse. Again, there's only the yeah, it actually makes it worse. So why is that? Just to be clear. Yeah, by like 100 milliseconds. Like, you may ask yourself, oh, why is it that parallelizing this loop doesn't make it faster? And it's because there's a setup cost to parallelizing, right? Especially when you're doing like a max on all of them. If the work isn't as hard as the time it takes to set up all your threads and your your locks and your stuff like that, and then use those locks, right? Because we're using max, it may be easier just to do it on a single thread. So yeah, it turns out that doesn't help. Um, Again, we could essentially use the same thing part 1 and part 2. So we can probably change this parse to return also a vec of stir. So we go like that, and then we say let. I guess I can just pull it from right here, right? And then we return happiness index people like that. That probably just works right out of the box. This one I have to do mute though. like that. Type annotation needed. That's funny that it needs it now. Okay, so now we've just changed our parser to give us both the hash map, the happiness index, and the people. And so then in part 2, I just have to add myself to that list. But then I can use this function, so we can just do like solve happiness index people to be the answer to part 2. I'm gonna do fn solve happiness index is a hash map of stir eye size and people is a vector, and we'll return an eye size, and then we just run this. What am I missing here? What did I do? Oh, not that right there. What doesn't like? Oh, am I missing something still? Oh. Like that. It didn't like it because I had both of them in there. Okay, that should give us the same result, right? 709,668. 709,668. Yeah. So there you go. We've already used it in both places. We have our parse function. It again, we gather the happiness index, and then we gather the unique list of people, and then we can pass that to calculate happiness, which just does the same thing. We go through all the permutations, and then the mapping is just turning the doing a window of each of the people, going all the way around, and then chaining the last and the first together. And so we sum up all those values, return the max of those, and that gives us part 1 and part 2. Okay, there you go. Not too bad complex wise. Again, if I'm solving it, we're in like the 40-minute range. I'm pretty sure that's super slow for competitive programming. So as I'm thinking about like how to improve my speed, some of it may be, obviously we did a lot of refinement. But again, if you like look at the times, part 1 took me 30 minutes. Of course, I didn't start it till about 7:50, but I read the problem, right? So I guess I can show you right here. The intro was only 1 minute. It took me 30, so it was like 29 minutes to solve part 1. And just a few for part 2. I probably could have solved part 2 way faster. So anyway, things to think about. I'd love to hear your input. Maybe if you're into competitive programming, I did get a couple of like books on it that I've been reading. But if you have thoughts or ideas, I'd love to hear it. Otherwise, we'll talk to you next time. See you for day 14. Bye, everybody.